Hello, everyone. Thank you for joining us today. And my name is Riza Fazili. I'm a PhD student at INRS and part of IEEE student branch here in Canada. Today, we are hosting Dr. Pedram Abdolghader to learn about hands-on machine learning with Python. Dr. Abdolghader finished his PhD in atomic and molecular and optical physics at the University of Ottawa in 2021. His research was on coherent nonlinear Raman microscopy and the application of deep learning methods to extract quantitative information. During his studies, he was a visiting graduate research assistant at Molecular Photonics Group and Computational Laboratory for Energy and Nanoscience at National Research Council of Canada. He is currently a research and development scientist at Fuse Cycle Incorporation. So thank you, Dr. Abdolghader, for giving us some time. The stage is yours.
Hi, everyone, and thank you for a nice introduction. So today we're going to start about learning some few basic things about machine learning. So here's the outline. So everyone can see my screen, right?
Yeah.
At least. Okay.
Yeah, we have your screen. Thank you.
Here's outline. So in the first session, I will introduce machine learning, linear regression, cost function, some gradient descent as optimization method, generalization, overfitting, underfitting, feature engineering, and we're gonna do today a practical example of machine learning in Python. On the second session, I hope we can cover k-mean clustering algorithm, principal component analysis, and also we're gonna do all those things in a Python, implementing some codes. And the last session, I hope we could cover a brief introduction about neural network and also convolutional neural network, then a denoising autoencoder, and in a practical example, we're going to use Python to combine all three sessions in a single project. So there are two really nice references, which actually I started learning machine learning from these two. The first one is a really 100 pages book of machine learning. It's a really brief book, but I mean, it's a good point to start. And the second book, which the name is Deep Learning, is like 600 pages book with all mathematics detail and everything someone needs to know if you want to join to the machine learning community. So the good thing is that the second book is free. You can download every single chapters on the website below. And one other thing, the author of the book, the second person, Yeshua, he called as father of machine learning. He's in Montreal, Polytechnic University of Montreal, I guess. So maybe also you can have a chance working with him. So because he's so close to us. So first, I'm gonna give some definitions about machine learning. In 1959, Arthur Samuel defined machine learning as a field of study which gives computers the ability to learn without being explicitly programmed. And the second definition, which was in 1998, Tom Matschel, or I can't pronounce his family name, came up with a new definition. A computer program is set to learn from experience E with respect to some task T and some performance measure P. If its performance T as measured by P improve with experience. I mean, it might look a little bit complicated, but when we're going to solve some problems and coding, you would understand this better. And also you can find these two references. I mean, there are two papers. The first one was with IBM, and second one, I mean, I just cited here for anyone who's interested. And one more thing, I will share all those PowerPoint slides at the end of session, plus the codes. So here, first give some motivation that, I mean, why machine learning became prominent these days. I mean, you can find applications in medicine, finance, chemistry, defense, social media, virtual reality, fraud detection, drug discovery, physics, computer vision, and many other things. So, uh, and also I provided some really nice example of some recent machine learning development. So this field of machine learning is called a natural language description. It means that the computer can understand what you are saying. In this example, which has been done by the OpenAI company, just by describing the computer what you are looking to paint, the computer start painting for you. For example, let's go to the web page here. So maybe now I should share this one with you. Pause sharing, then I will share something again. So Google Chrome. Oh, okay. You can see the page, right? So here is the website of OpenAI. So as you can see, there's a model which trained based on human language. So as you can see, I mean, it converts the text description to the images. And now just let's see this one. An astronaut riding a horse in a photorealistic style. You can see the computer gives the right side image. Now let's change this one to the a bowl of soup, then a planet in universe, and digital art. So all these images are created by the computer. And one amazing thing about that is these images never exist and never painted but by someone before. I mean, the computer is just imaging this one. I mean, painting these things. By just changing the word here, you can see a different combination. I mean, it's kind of transferring the text to the images. So this is one of the hot topics which OpenAI company is working on it. And I will have another example for you. I mean, this one was interesting for me. That's why I shared it with you. So let's get back to our slides. Okay. So another example, which I'm going to show you is this one. Uh, this image was also created by computer by just typing, giving the text to the computer. So as you can see, if someone look at this at the first sight, he might think that this one was drawn by artists or someone else, but it's just a computer work. So, and the third example, which I'm really interested in this one, is here. So you can see by just describing the computer that what image I'm looking to create. So as you can see, you telling the computer, I'm going to put a women with short sleeves shirt in a maybe kitchen with some lemon on the shelf. And also, I mean, all the details here is just in a real time. You tell into the computer and it start generating these images. So, I mean, these are two important projects of the OpenAI company. So another nice example is real-time machine learning, which has a classification. So as you can see here, oops. This video, I mean, in this model, the computer use YOLO algorithm. YOLO algorithm is an object detection algorithm. So you can see in a real time, I mean, if you just have a camera and install your model on your cell phone, in a real time, it can tell you, I mean, the objects that is seen by computer refer to what? For example, I mean, the truck, the bus, a person, or whatever. I mean, you can see also traffic light. So, and it's really interesting that in the real time, you can classify things just by video. And this video has not seen by the model because later I'm going to explain how you can train the model. So one way of training model is that you will give the computer or the model thousands or millions of examples. Then the computer learn features of those examples. and then you fit the computer or you fit the model with the new data set, which has never been seen by the computer. So this is actually the critical ability of machine learning, prediction of some things that has never seen by the computer. So usually people classify machine learning models into in four categories. One of them is called supervised learning. Uh, the other one is called unsupervised learning. Third one is semi-supervised learning, and the last one is reinforcement learning. In these three sessions, we are going to focus on the first one and the second one. So here I'm going to give you an example or definition of what supervised learning is. Supervised learning is a task of learning a function that map an input to an output based on example input output pair. So here just look at the very simple example of linear regression. You are trying to fit a line to the data set you have. So your y values depends on just one variable, which is x. So, and the data sets presents by the blue dots, and we are going to find a line or the model that maps this data set. I mean, just simple linear regression. So, uh, so let's have some definition. The data set. Data set is a collection of examples, each of which is made of features. Uh, a design matrix or model matrix is commonly used method for representing a data set. For example, now imagine that you have a data set of three examples with each having three features. This can be representing by a design matrix which has a dimension of R4 to the 3. So here you can see the design matrix. So as you can see, Y1, Y2, Y3, and Y4 are labeled of our data. X1, X2, and X3 are features of our data. Now, maybe I should have a pen. So Y1 is one example. And this example depends on three variables, X1, X2, and X3. Again, we have Y2, which depends again on the X1 value, X2 value, and X3 value. This is called design matrix. So it's just way of representing your data set. And in supervised learning, we are trying to have, I mean, the data set we are giving to the computer is like X, Y, which we know that, for example, in this example, X is also a three-dimensional vector, which is X1, which is X2, and which is X3. So here is an example of linear regression. So you have a feature vector. I mean, the feature, we are referring to the feature vector. For example, X1, X2, and X3. I mean, this is called feature vector, which could be n-dimensional. For example, you can have feature like X1, X2, and so on to Xn. This dimension could be thousands, even millions. And you have an output, which every single output refers to one X, refers to one example. For example, I can call this feature vector as X1, X2 to Xn refers to example number one. Then for the next example, I can have this one, let's say this example number two. I can have X12, which means that the feature of sample number two and the first dimension. Again, X2, 2, again, X2, 3, and so on. And every of these examples are related to the Y, to Y1. Y1, this one was Y2, and this one refers to as Y1. So here you can see the data set. Here I assume that I do have n examples. N examples, which I know that what feature belong to what target. I mean, the Y can be called as target or output value. So in a machine learning model, generally we are trying to map a function or find the function that maps the target, the Y, to the features. Here you can see, I mean, because we are going to use linear regression, so I assume that we are using a linear function. So Y, the target value, is related to the feature vector by some weights here. So, and the goal of machine learning is to finding these W, and T here is just means transpose. I mean, it's coming from linear algebra because of multiplication between two matrices. I mean, T has no significant meaning. So the, okay, so now maybe in this example, things become more clear. So now here, you can see, just imagine that we do have n number of examples and we do have 4 features. It can be like a person feature. For example, we can say that x1 is how tall he is, x2 is the weight of that person, x3 is eye color, and x4 could be the race or gender. So, and y can be labeled as, for example, I mean, by considering all those features, this number 4 can be, we could say that a person belonging to group number 4, this one person belonging to group number 2. I mean, based on the features, we relate the feature vectors to a target, which is called y. So as you can see, data sets defined as xy, an example of these things, and the feature vector, which here depends on 4 variables, x1, x2, and x3, and an output. So, and the goal of machine learning is to finding the W. The goal of linear regression here is to finding the W's. But in machine learning, we also have classification. Linear regression was just one model. Was just one model of supervised learning. We do have also logistic regression or classification. I mean, both terms are same. So it means that now imagine on the left side of the picture, we have labeled data set. We know that the first image is a dog, the second one is a cat, third one is a dog, and so on. Now just imagine we do have 1 million of these images. So then we feed all these data sets to a machine learning model. And then for testing if the model is working, I mean, we call this term as a training. We train the model based on the input data set, which input data set is the data set on the left side of the slide. And then for checking the performance of a model, we then give the model some data which have not seen by the model before or during the training, which is unseen data set. Usually this is called test data set. Then after, the model can predict, for example, the first example which was given to the model referred to a cat. The second example which was given to the model refers to the dog, and third example which was given to the model again referred to the cat. So this is another application of machine learning or another model of machine learning, which is called logistic regression or classification. This also can be used as cancer detection. These days also people do cancer detection based on logistic regression or classification. For example, you can record thousands, millions of images from a healthy cell and thousands or million images of a cancer cell. Then the computer, the machine learning model can find features of a cancer cell and a normal cell. For example, a cancer cell might have different size. I mean, all the cancer cells might have, let's say, 2 micron size, and all healthy cells might have the size of 2.1 micron, or other features. Maybe, I don't know, the Raman spectrum of the cells might be different. The intensity between peaks of the Raman spectrum between the in the cancer cell and in just a healthy cell might be different. So these are all called features. And then the machine or the model can predict or classify between a healthy cell and a cancer cell. Uh, but we do have also another model, which is called unsupervised learning. In unsupervised learning, the model, by seeing many examples in the data set, attempts to learn shared feature amongst the example. It tries to learn the feature probability distribution. Data clustering is a data analysis approach which groups objects that have similar features. A common unsupervised clustering algorithm is called k-mean clustering, which we're going to implement this one on the second session. So now just look at the picture on the left side. I mean, here you can see 20 dots, 20 black dots, which every single one is an example, which depends on two variables, x1 and x2. For example, for the dot number 1, x1 feature equals to 40 and x2 feature equals to 10. Or for example, for this point here, the x2 equals to maybe 32 and x1 equals to 49. So in the previous method, which was supervised learning, the computer was given based on labeled data. So the computer knew that feature x1 and x2 will be assigned to target y. But here the computer has no information. I mean, the only data set that you're giving to the computer is just this. You will give the computer just some features, and then applying a clustering algorithm or unsupervised algorithm, you end up having making them in a groups. For example, this section here belongs to one group. This section belongs to the second group, and this one belongs to the third group. And the difference between supervised and unsupervised one is just here, because in the unsupervised one, we never tell the computer that, for example, this group here belong to, let's say, group number 1, or this group here belong to group number 2. The computer itself or the model itself start to find a feature which is common between the examples. For example, the common feature in the, let's imagine the first group here. The common feature is that all these points, I mean, the examples are the distance between the red points to the star, which is center of the cluster, is much closer than the, I mean, for example, this distance is much closer than to this distance. So this is why we call the first one as a first group or first cluster. And again, for here, I mean, the common feature between the examples in the second group is that the distance between examples and the center of the group, which is called centroid, is much closer than the distance between this example to the center of the third group. So you can see the algorithm automatically, I mean, can understand this, I mean, which is called, it finds a feature probability distribution. So, but the main question is that, let's get back to the linear regression, the simplest one. How to find the weights. I mean, here, how we can find these weights. So here it is. So just as a quick review, we do in training a model, we do have two sets of data set. One of them is called trained data set, and the other one is called test data set. When we are saying trained data set is using for training the model. So I mean, over many iterations or over many epochs, I mean, iteration is called epoch in machine learning. Over many epoch or iterations, trained data set fit into the model, and after a while, the model or the parameters, the W, the unknown parameters will be found. But the test data set is using after training a model. It means that after you train your model, then you feed your model with the test data set to figure out how accurate your model is. So this is the difference between test and trained data set. So now for finding a W's, we need to define a cost function or objective function. Cost function or objective function, now we are talking about supervised learning. It means that what's the difference between actual data, I mean, I called this W as actual data, I mean, these are exist in the training data set. I mean, this data set belong to here. We have them already. The difference between this and the difference between output of the model. Here, y hat refers to the output of the model. What output of the model is? Output of the model was W transpose multiplied by X. So it means that if the model get the X input, get the features input, what would be the output of the model? So actually it's just mean square error. I mean, it's one criteria, one objective function which usually used in linear regression is mean square error. As you probably know, what's the definition of mean square error? So we calculate the difference between we calculate the mean square error between the output of the model during the training and the actual value of the data set. I mean, actual value of the data set is called y train, and the output of the model is called y hat train. And then we take an average over m, which m is number of examples. So as you can see here, the goal of training a machine learning model is to minimize the cost function. It means that if we can minimize, if we can make mean square error close to zero, it means that the output of the model, I mean the predicting value of the model, would be quite similar to the actual value of the data set. So that's why the goal of training a model is to just making this one as small as we can. So, and for doing this, there are some methods exist. So as you know, how we can minimize the mean square error? Derivative always help. So if you remember, I mean, in the high school, we always take the derivative of a function and it gives us a minimum of a function. I mean, it gives us the minimum and the maximum, but now we are going to focus on just the minimum function. So we need to do a lot of derivative. So in this case, I did that. So I mean, actually, I stole these calculations from the reference book number 1. So if you take the mean square error, which I just defined in the previous slide. Let me get rid of this bit. Oh, here. If I take the derivative of mean square error respect to the W, and why I'm doing this, let me show you. Because mean square error was defined like as this one, right? And we know y hat equals to W transpose multiplied by X, which W is unknown parameter or the variables of our model, and X are the feature vectors, which we do have them from the training data set. So we are going to calculate y hat minus y and then square. So taking the derivative respect to the W and then equally to the 0 gives us the minimal point of that function. So now if we just expand this one here, W hat is equal to y hat equals to W transpose X minus y square. So we are going to take the derivative respect to the only variable of our function, and the only variable of our function is here W. So we have it here. So after taking the derivative and equally to the 0, we end up finding this term. So it requires 1 page of calculation, but for just save some time, I wrote the final answer. So then W equals to X train transpose multiplied by X train reverse, then multiplied by X train transpose and Y train. So it gives you the weights that minimize your cost function or minimize your mean square error. So briefly, we can say the performance of a machine learning model is evaluating using the cost function or objective function. This term is true always for all machine learning models. We need to calculate the cost function, then minimize it, try to minimize it. So in my opinion, machine learning is just optimization problem. You are trying to minimize the cost function. You are trying to make the difference between output of the model as close as the actual value that you know already. So many machine learning techniques use optimization to determine the model's parameter by minimizing the cost function. Okay, different cost function exists depending on the application for which the model will be trained. For example, for linear regression, mean-square error is the best function to be optimized. But for classification, I mean the cat versus dog, the best cost function is called cross entropy, which I mean is beyond the scope of our talk. But I mean finding the suitable cost function depends on the application, on our application. Like as in classification, we need to use a logistic regression. For linear regression, we need to use mean-square error. There are various methods for optimization, the most common of which being gradient descent. So this term is a general term. Just imagine that now, I mean, the linear regression or classification was the simplest model in the machine learning that you have seen. But you can find, I mean, in the third session, we are going to introduce neural network. So in neural network is a much complicated case of machine learning than linear regression or classification. In that case, you might have a function to be minimized with million of parameters. So then mean-square error or other objective function would not be really practical. You need some complicated or some fancy way of optimization, which one of them is called gradient descent algorithm. But about gradient descent algorithm, we are going to review that. Yeah. So actually, gradient descent is an iterative optimization approach for determining the weight value which minimize the cost function. I mean, if you again recall this one, W hat was equal to, sorry, Y hat was equal to W transpose multiplied by X. The goal of machine learning was to finding these weights, right? So, and we told that one way of, I mean, the cost function is defined as 1 over M, which is kind of getting average over the examples. M is the number of examples of the data we have. And then Y hat, the output of the model, minus Y, the actual value of our data set, then squared. So it was a cost function which we were going to minimize that, right? So now instead of using normal equation, which normal equation was this one, right? Instead of doing all those derivatives, because here the way I found, or the author of the book found the exact values of W was based on analytical solution. It means that he did the derivative and then set the function equals to 0 and then found a really exact mathematical term. But in 99% of the optimization, this is not the case. We can never by hand do the mathematics and take the derivatives. That's why we are using numerical method. And one of the super powerful numerical methods is gradient descent. So now for simplicity, let's imagine that we have a function which depends on only one variable, y equals to fx, and x is only single variable. So we are going to minimize this function using gradient descent algorithm. So if we add a small value, epsilon is a really small number. If we add this value to the x, then we can approximate our function by fx plus epsilon multiplied by f prime x, which f prime is a derivative, as you know. So then we will set x, the previous x, equal to, sorry, this is a new x, to previous one minus epsilon multiplied by f prime x. Actually, it's just definition. This one is just definition of derivative. F prime x, if we just write it down in this way, equals to fx plus epsilon minus fx divided by epsilon. As you can remember, in high school, we had that epsilon was equal to x plus epsilon minus x, and we had the limit here. So this is basically just that one. This is the definition of derivative of x. So, but why this is working? So now look at this figure. So let's discuss about the sign of f prime. Now imagine that the blue line represents y equals to x squared. As you know, there is a minimum at x equals to 0, which tells us the minimum of our function. I mean, x equals to x squared has a minimum right at the 0. I mean, this is something that we know. So if you can see, the function f depends on x minus epsilon multiplied by sine function f prime x is always smaller than fx for small values of epsilon. But why this is true? For example, let's just see this part of our function before x equals to 0. Here, all the derivative of the points, I mean, these are just a slope of the function, which means derivative. So all the derivative have the minus sign. You can see all these, I mean, this one, this one, this one have the minus sign. So it gives you here as a minus. So minus of f or something. Then you are basically, you have a minus here. So minus multiplied by minus gives you the plus. So it means that you are moving your function from this one to this point, or from this point to this point. I mean, by adding the small value to your function, the epsilon, because of the derivative sign, you are getting close to x equals to 0. Now look at this part of the function. So here, all the derivative are positive values. So, and you can see, I mean, this represents the x. So here, the sign of this one, I mean, for the points bigger than x equals to 0, this sign function gives you the plus sign. I mean, sign of f prime x would be +1. So x minus epsilon always decreasing the value of function. So it gets that to here. So over some iteration, you would end up finding your minimum point here. Just because of the sign of derivative. So as you can see, for x greater than 0, the sign of f prime x gives you the positive value. So fx minus epsilon would be a smaller number. So because it's kind of decreasing based on the f equals to x squared. And for the x below 0, you can see the sign function of f prime x gives you negative value always. So negative minus negative would be f x plus epsilon. So, and if you add, I mean here, if you add a small amount to the x, let's say x plus epsilon, you would end up having the smaller values here. I mean, the value of f decreasing to the 0.
So epsilon is always positive, right? Epsilon is a positive small value, but it's positive.
It's always positive, yeah. This epsilon is called learning rate. So we will discuss about it in a few later slides. So, but also there are some challenges using gradient descent. I mean, all the functions are not as simple as f equals to x2. Now imagine that you have a function that looks like, I mean, this one. So you might have different minimum and also some points that, I mean, the f prime is equal to 0. For example, here, this is called saddle point. It means that the f prime x equals to 0. So you can see here representation of some local minimum and global minimum. Actually, when we are saying global minimum, it means this one. It means that there is no point in the function which has the smaller value of f. So this value of x gives the smallest value of f. This is called global minima. But we also do have some other minimum, which here and here, I mean, these are called local minimum. And the goal of machine learning is to finding the global minimum. I mean, if we cannot find that, then we're going to the first local minima or the second local minima. So this makes things a bit complicated, and because you're dealing with functions with multiple variables. Now I'll just make things a little bit complicated then. In the previous example, we had just f depends on x, I mean on one variable. Now imagine that I just added one more parameter to my function. Now the y hat, the model, equals to f x1 and x2. So this is called, oh sorry, and x3. So now we have a function which depends on x1, x2, and x3. Now just by plotting and just looking at this one, you can see the things are so complicated. You have this local minimum here, you can have this global minimum here, which you can see no points is less than here, which is called global minima. You can have a saddle point here. The saddle point is just called the point that has derivative equals to 0. So, and in a real actual machine learning problem, you're dealing with millions of parameters that involve in training a model. So that's why the solution is using directional derivative. I guess we are all kind of familiar with directional derivatives. So, but I will give you introduction. So this is called directional derivative. It means that we are taking our derivative respect to the vector. Now imagine that here we have a function. This is called j, or our cost function. We are trying get to this point. This point is called minimum of our function, minimum of our cost function. So as I told you before, the goal of machine learning is to minimizing the cost function, is to minimizing the difference between prediction value and the actual value. So this is why we need to use derivative. Now here we are getting involved with the gradient. So gradient is a vector, as all of us know. Gradient defines partial derivative respect to the I hat, partial derivative respect to the j hat. Now you can see two derivatives getting involved here. So, and again, but the principle of algorithm will be kept same. You can see x always, I mean, we first need to take the derivative respect to the vector, to a unit vector, and then minimize that function. Now we are dealing with the cos theta, which is just kind of normalizing a vector. I mean, it's just minimizing a surface, finding a minimum point, and then x substitute by x minus epsilon, the learning rate, and the derivative respect to the x. And now this derivative x, this x means that the vector, which is x1, this is x2, which is x3. I mean, or it can be go up to thousands, million of parameters. So let's skip this one for now. Just go to the practical example. I mean, the Python one. We are getting close to dive into coding. So there's
just
a practical.
One question.
Sure.
That's one question. If what if we get stuck in one of those local minimums? I mean, just the accuracy of the script, the technique goes down, or it just doesn't work?
Usually it happens. You will stuck with local minima, or even you might stuck in other points. This is why now there are some people working on just algorithm developer. So they are using papers, just writing down equation and try to solve that. I mean, it's a really hot topic in machine learning. For example, now we are using gradient descent, but in training neural net, we're using gradient descent, but in a very advanced way, which is called Adam's algorithm. So, I mean, I can tell thousands of algorithms exist. So that's why, yeah, you're right. I mean, usually, I can say always we stuck in the local minima. So, but there are ways that we can get around that. I mean, just defining new cost function, defining new minimization algorithm. So this is actually a hot topic, I mean, in machine learning.
So if we get stuck in a local minimum, just the accuracy would go down, right? I mean,
accuracy will go down.
Okay, but still it would work partially. I mean.
It would work, but it might end up giving the wrong answer.
Ah,
It depends on your application. Yeah, you're right. So if you don't need that much accuracy, yeah, it works. But for example, imagine if you are going to tell either a cell is cancer or healthy. So it's 50-50. If you tell it wrong, then the patient will die. So here is a practical example of training a model with gradient descent. So here I used a synthetic data set with 200 example, which was generated by computer. The data set are as X, Y, and Y1. I mean, we do have 200 of this, which considered as a sample, and it is shown here. I'm going to find a line, a linear regression line that fits all these points to that with Python. So as you can see, the linear regression model looks like this, Wx plus B. I mean, you haven't seen this B before, but this is just bias term. So it defines this point. I mean, from what point we can, so we can also combine this one to the W. So this is just like the previous one, F equals to W transpose dot X. I mean, there's no difference between these two. So the cost function equals to, again, mean square error, Y minus the prediction value. I mean, this is the prediction value of our model, because, I mean, this is just linear regression, right? Y was equal to Wx, and this Y are from data set, from the synthetic or generated data set. Then we calculated, then we take an average over 200 example we do have. So we are going to apply gradient descent algorithm to minimize this function. So I just took the derivative, I mean, the cost function respect to W, because we do have now two parameters, W and B. So this is our model. So we need to minimize this W respect to two variables, W and B. So taking derivative of cost function respect to W give you this one. Taking derivative of cost function respect to second variable gives you this one. Then we need to plug in the new values to the old value. So this one is the old value. This is the new value. I mean, new weight. And this one is the learning rate, alpha. Right, this alpha was like just epsilon, which I told you in the previous slide, Fx plus epsilon. I mean, this is called learning rate. So, and same as for B. So we are going to do this over a lot of iterations, so which is called epoch. And also for just starting our algorithm, we need to initialize the values, the parameters. First, I decided to initialize W equals to 0 and B equals to 0. But initialization is also a critical problem. But now, because we are dealing with a really super simple example, we can simply just initialize it with some arbitrary values, which I prefer to use 0. So what happened over iterations? So this is the first iteration. The model predict that this line's fitting this, which you can see is obviously wrong. Then after maybe 200 iterations, the model gives this one, this line fits the data set. Then after 1,000 iterations, this gets this one. Then after maybe 30,000 iterations, the lines gets to this one. So you're going to see this one. You're going to do this by yourself in Python. So, and now this represents
the iteration. You mean the number of samples, or
iteration? It means how many times we are applying gradient descent. Because as I told you, gradient descent is an iterative method. I mean, it's gonna be done over many iterations. So for example, in the first iterations, you will find this function or this model, which is wrong. After 200 iterations, you can find this one, which you can see it's much closer to the reality. Then after 2000, this one, then after 30,000, this one. So, and this plot is number of iteration or epoch over the mean square error. So you can see, I mean, 10 to the 0 means that 1. So at the first iteration, our error was 13. Then after 10 iterations, our error maybe is like a bit smaller than 30. After 100 iteration, our error gets down to 10. After 1,000 iterations, our error gets close to the 2. And if we continue this one, we end up having this. So the time we need to stop our training is when we get this plot. I mean, you can see that if you continue the training, the error value doesn't change. So here it means that you found either a global minima or one of the local minima, and you cannot do much about that. So you need to stop your training. And if you don't stop your training, you would end up overfitting problem, which I will explain you later. So I guess now is the time to go to the Google Colab or maybe Jupyter Notebook, whatever you prefer. I personally prefer to use Google Colab for Python because of 2 reasons. One of them, which is most important, is free online platform. The second one, it provides you free GPU. So you do not need to buy graphical card for your computer, and it's free for 24 hours of continuous working. And when you are going to train a neural net, absolutely you need a GPU. I mean, if you're gonna train, let's say 8-layer neural net, it's gonna take on CPU, it's gonna take like 6 hours. But if you use GPU, the time reduces to 5 minutes. So now you can see the big difference between using GPU and CPU. So, and the third one is it also provides TPU, which is called Tensor Processing Unit, which I have no idea what this one is. I need to also go and learn about that. But just I heard that this one is much faster than GPU. So maybe later we can learn this one. So, the question, is it always good to train the model using huge number of iteration? No, the answer is no. Why? Because we end up finding overfitting or underfitting issue. The crucial challenge in machine learning is that trained model must not work only on the training data set. As I told you, when we start training a model, we're feeding the model with some input data set, which is called training data set. But machine learning is not just linear regression, or is not just regression, but that just seeing some data and predicting the relation between and mapping a function to those data. It has also be able to predict values or to classify values that has not seen by the computer or the model before training. So it means that if you train your model based on 1,000 examples, let's say I have example number 1 to example number 1,000. So I give them all to the computer, the model trained, you found all your weight, I mean the W's and everything set. But if you give another example, I mean from another data set which wasn't used during the training, your model has to be able to also work on that data set, which is called test data sets. So this is the difference between machine learning and regression problem. That's why it makes it unique. And the reason why we can train a model on some data set and the model can work on the other data set, the answer is in the statistical learning theory, which is really something complicated. I can maybe share you a book later, but I really have no idea. I just read a few pages of that and I didn't understand nothing. So, but I can share you the book, I mean, if you are interested.
This overfitting and underfitting issue. Oh, okay, you will explain later. I wanted to ask if it's related to the speed of learning also or not.
Yeah, speed of learning. So it's not related to speed of learning, it's related to time of learning. So if you continue the iteration, let's say your model can be trained in 10 minutes. If you continue the training, let's say 1 day, then you end up of overfitting. Why? You can see in the next slide. Now here you can see in here you have underfitting. It means that this point and this point. I mean, if I assume that this straight line is my model prediction, but this line cannot predict this point and these 2 points, right? This is called underfitting because my model is not able to also predict another data set. I mean, it's kind of telling that, I mean, it fits to these 2 points, but it's not fit to these 2 and these 2. This is called underfitting. Here you have overfitting, because you can see it's predicting all these points, but also you can see it's telling you 1 point exists here, 1 point exists here, 1 point exists here, which is wrong. You can see no points here. So this is overfitting. If you continue your training for a long time, this end up this one overfitting. But if you continue your training in a suitable time, then you will have this one. This is the best training. You can see the model, the curve line can predict this point, this point, this point, this point, this point. I mean, it predicts all the points. So machine learning performance should be good for both training data set and test data set. So
I really like the pictures on the left. I mean, it's
very,
very more clear
accurate.
actually. I didn't check the graph. I just checked the Tom and Jerry, and I understood. Okay, this is the orbiting. This is
the left one at the top means that when your model performance is just good on your trained data set, you might think that it is working for everything. But in reality, maybe you train the model that just working for your trained data set. It's not working for other data set, which is a failure in your training. So, where we are. And also, we need to do some feature engineering. So before fitting our data set, we need to normalize it and also making it a standard. And normalizing means that we need to subtract the mean value and also dividing by the standard deviation. Standardizing means that we need to subtract the mean value and divide it by the standard deviation. These two helps for speeding up your training, because I mean, your features might be a number like 10 to the 6. So it means that you are using a lot of bits in your computer if you are dealing with number as big as this one. But if you just rescale these numbers, I mean, something between 0 to 1, it means that you are using less memory. So you are calculating with more efficiency. So these two things are important. The first time I was training a model, I forgot doing this one. My cost value was about 10 to the 4 or 10 to the 5. And then just by adding this term, by just doing normalization, my cost changed to 10 to the minus 4. So you can see big difference. And also 5 hours of training versus just a few minutes of training. So I think now we should go to the Google Colab. For going to Google Colab, you need to type. Let me stop sharing this one. Oh, we have 2 questions. Oh, sorry. Please leave your question in the chat. Okay, this is not mine. Okay, so let's share. Oh, okay, the Reza did that. So let's go to the Google Colab. Everyone knows how we can go to Google Colab?
I put the link in the chat so people can.
Okay. So maybe we can have 1 or 2 minutes break and then start the coding in the Google Colab. So for using Google Colab, you need to have Google account. So if you don't have it now, maybe you can make it quickly, or maybe you can use Jupyter Notebook. I mean, as your convenience. So it's not necessary using Google Colab, but I already did that, so that's why I'm using this. But you can use Jupyter Notebook, but for the third session, it's really necessary to using Google Colab unless you have GPU on your computer, because then we can finish our training in 5 minutes and you can finish your training in 5 hours. So we can have a break for 3 minutes.
Yeah. If everybody can sign in over there.
Shall we start?
I think we can continue. Yeah.
Okay, can I start?
Yeah. Sure.
Oh, and everyone can see my screen, right?
Yeah.
Okay. So here we are going to do linear regression in Python. So, and using gradient descent. First, we need to import the libraries. The good thing about Python is that there are many libraries that people already wrote that before. So we are just going to use them. For example, NumPy is a really powerful library for doing calculations and mathematics stuff. And Matplot is also a great library for plotting our results. So I just need to type import numpy as np, which means that when I'm saying as, it means that anywhere in my program, I do not need to type numpy. I just need to type np. So again, here we are telling to the computer import matplotlib.pyplot as plt. So instead of writing down all these long words, we can just use plt, which is calling this library. So let's first we need to connect to the Google Colab kernel. So here you can see it's connected. Let's run this one. So you can see a green tick on the left side. So it means that these codes is implemented successfully. So if I'm going so fast, you can stop me. Second, we need to generate our data set. So the first line here, np.random.seed1, it indicates that every time in my program, if I call a function that generates some random numbers, it generates same random number. So this is why I use this line of code, np_random.seed1. So x equals to np. It means that we are calling numpy library dot random, which is the syntax, dot rand 200, which means that I'm going to generate, and this rand means that it means that picking from a distribution, from a normal distribution. I mean, if we just use random, it picks from something really random. But if we type dot rand, it means that it is picking these 200 numbers from normal distribution. And x equals to 3x plus np random dot rand 200 plus 3x np random dot rand. The reason I put these three here and these two here is just arbitrary. You can put it 4 or any number you would like. I'm just going to define a function, define my model, right? So, and here after this, I mean, this np.rand.random.rand, these are my weights. These are the W's that I'm looking for find. And this term here, this is the B, which I'm going to find it. So first we initialize them with a random number. So let's run this one. So then let's just see how our data set looks like. So I'm going to use matplotlib library. So, and also, I mean, here, the first line of code is just making the plot fancy. I'm importing the patches, import the shadow. I'm going to make some shadow in my data set. I mean, here in the legend, you can see there is a shadow. So I just made it fancy. You don't need to, I mean, if you don't write down this code, nothing's changed. So, but let's just for making beautiful, keep this one. So plt.scatter, scatter is a function that plot scattering like as Excel. So the argument of this function is x, y, and also you can add the label, a legend. So, and label equals to data set. So the name goes to a quotation. Plt legend, then here we are defining size of the legend, the shadow, and also the position of this one, the position of the legend. So by changing these two numbers, this refer to X and this refer to Y. So by changing these two, you're basically changing the position of this legend. So, and also we are going to define the tick parameters here, the ticks here, here, and here. So I decided to have with the width of 2.5 and the length of 4 in the inside direction. As you can see, the ticks are inside. You can also change this one to out. So, but let's do it with inside. Then we are going to define the tick font size, which is 16 here for Y, and for the X also 16. And we need also label our axis. So Y, which any name goes to the quotation, Y label and X label with the font size of 6.5. So let's run this one. So you can see this is our data set. Let's change this one to the out. I mean, I've never done that, but we have time. Let's try to see if it works. Okay, it works. So the direction can be in, out. Let's try the middle. I've never done that also. Okay, there's an error. So we have just option of in and out. So let's put it in. Okay, and now we are going to define the training function. So in programming, you usually try to use block of function. For example, if you see here, I mean, in Python, when you are going to define a function, you use def, the name of the function, and the variables of the function. So the train depends on X, Y, W, which was the weight we are looking for, B, something also, I mean, the parameter I'm looking for, alpha, which is learning rate. I just named them as the alpha, and epoch with number of iteration. So here I defined two lists. I mean, in Python, this refers at the list, and this one refers to the dictionary. So usually when you are dealing with numerical things, better to use list here in two quotation. But when you are dealing with label and numbers, better to use dictionary. So the first one is list and the second one is quotation, because in the list I'm going to append the error value and the parameters. I mean, I'm not going to label error number 1, error number 2. I'm just going to keep the values of the error. So it's better to define two lists. So the first list is train error. We have a question. Would you please share the code, or if it's possible, please copy and paste each cell so that we can run it with you. Oh, it's a good idea.
That would be better, yeah, actually, if they can do it right now.
We have time. We have 1 hour time. You can just, I mean, see my screen and type your codes if it works. Also, I can share, but I don't know how to share it with you. I can send the Python file here if it works.
You maybe we can, I mean, it's fine also. I mean, we can, after the session, we can just send it to everybody. I mean, via the IEEE website, I can just send them and they can try it after the workshop. Or
yeah. Definitely I will share the codes. But you know what I was thinking? I was thinking that maybe you can divide your screen to two parts. You can see the codes on the left side and on the right side. This is why I told you before that I'm going to slow. I mean, just run them.
Yeah.
You can type fast. So
yeah, it's fine. Yeah.
Let me try. Maybe here I can share the Python code. I mean, I can do it quickly. So it takes 1 minute. So save. Oh, download, sorry. I can download it as a Python file. So here, linear regression, then just file here. Oh, I guess it's doable. Google Drive.
I think you saved it on the piece on your laptop, huh? It's download.
Okay, you mean it's better to continue?
No, I think you already downloaded there, and it's
Oh,
down
did
there.
I?
I think yeah, I think it's saved in the
But I
the
cannot send it here.
you
Can I send you by email? Then you forward them to all.
yeah, maybe you can just send it to me, then I will.
Okay, so just give me a second. I need to stop sharing. I'll share it on Telegram with you because we cannot email it.
Okay. Yeah, I will drop it in the chat.
Okay, you have it now.
Yeah.
Also, I can wait maybe for 2 or 3 minutes that everyone can download it. Okay, you're here. Let's wait for 5 minutes so everyone can download the code.
I'm trying to share. I think just accept the link. It's fine. I will put it on some Google Drive maybe or something maybe. Yeah,
So,
the link is in the chat, so now everybody, they can just download that.
Should I start?
Yeah, maybe just wait 1 more minute, guys. They can. I think now we can continue. Yeah.
Okay. So we've been here. So just plotting the data set we generated. So let's do it again. You can see that here we do have 200 examples that depends on one variable, which is X. I mean, it's a super simple problem. So now we are going to define the train function. Train function in Python, we define it like this: def space name of the function and arguments of the function, which here is X, Y, W, B, alpha, which is learning rate. I mean, it was better that I wrote here learning rate, epoch, which number of iteration. So as I mentioned earlier, we do have two methods. Since Python is object-oriented programming, we do have methods. We call them methods, not functions. So here is a list. I mean, this one, the first one is a list, which is a perfect place to saving numerical things. The second one is dictionary. Is a perfect place to saving labels as well as numbers. For example, for a dictionary, you can say A equals to 10, B equals to 11 or something. This is something like that. But when you are dealing with a list would be just this, I mean, without any label. So since the train error is going to be just numbers, so we will use list here, and W parameter is the same, so it's just numbers. So here is a loop. Just one hint in programming, is way better than not using loops, because using loops also takes a lot of memory. So, but here our example is so simple. Usually what people does is that they are using vectorization. Vectorization is a super powerful for calculating. I mean, you would never use for or loops again if you learn how to do vectorization, which I'm not also so familiar, but I'm going to learn that. So here it says that for E in range epoch. So this is the way of defining a for loop in Python. So E is a kind of index, and in Python, index start from 0. It's not like MATLAB or C that starts with 1. So W and B equals to update WB, which now here you can understand. Here, this is a function which updates the value of W and B, and this function depends on five arguments. One of them is X, Y, W, B, and alpha, which is, I mean, X, you know, that is a feature, Y is the target, W is the weight, and B is the bias term, or also this W and B are both unknown parameters of our model, and alpha is the learning rate. So you can see in every iteration, because for E in range epoch, it means that it starts from 0. When it starts from 0, it goes and runs these 3 lines. Then it starts from 1, 2 until you hit the epoch number. So it could start from 0. To epoch number, which could be 1,000 or something. I mean, so, and as I told you before, in Python, or mostly in programming, it's better to use block of function. I mean, if I want to write down the update function here, or also writing down other functions here, you would end up having maybe 2 pages of definition of function, then can make things confusing. So, and also if you define functions separately, then you can call them in different part of your program. So here, I mean, I just wrote update WB function, which has 5 arguments, X, W, X, Y, WB, and alpha. And then in every iteration or in every epoch, append is a method or a function that add the cost function value to the training error. So in the first, for example, in the first iteration, let's say your cost or your loss function gives the number of 12, right? So in the first one, the train error would get this number, 12. At the second, because also this one is a function, the average loss, which depends on X, Y, W, and B. As I told you earlier, we need to define functions in a separate columns or in a separate part of our program. So in the second epoch, let's imagine that our error decreases to 10, the third epoch to, let's say, 9, and so on. So, and also we are appending the new weights, because in every iteration, in every epoch, we find the weight, and over the iteration, the weights value would get close to the actual one, to the real one, to the one that we are looking for it. So, and this part of the code here is just plotting the progress of our training. It says that if E, the number of epoch, divided by 400 equals to 0, then print the epoch number and the loss function. So this method dot format, I mean, in 2 quotations, you need to write down I mean, these lines of code, I mean, in these two, if you use this one, then dot format gives you the first one, e plus one goes to the here, epoch goes to the here, the second parenthesis, and average loss goes to the third parenthesis. And 0, 4, F means that up to 4 significant digit, printed up to 4 significant digit. So then your function, I mean, the training function will return WB train error and W parameters. Sorry, WB train error and W parameters. So let's run this one. So this goes to the memory. Now we define our training function. So for the next step, we are going to define the loss or the objective function. So def uh, AVG average loss depends on X, Y, W, and B. Um, First, we need to, we're going to use mini-score error, right? So here, if you take a look, this is, I mean here, this is a definition of mini-score error. W minus W hat, in a slide, you have them, you had them. W minus W hat, and then score that. So, but also we had divided over number of examples. So because of taking average. So here, when we are returning that value, we divide it by n, by float n, which float convert the number to the float, not integer, because uh, oh, there's no cause. It divides the error to the number of examples. So which here is 200. So this function basically here, which I'm going to run it, just calculate the mean square value between the prediction value and actual value on data set. Then return that one divided by number of examples, which gives you the average. So, and here is the updating function. I mean, as you can see here, we used W and B equals to update W and B function. Now here I'm defining the update function, but how I should define the update function is based on the slides that we have seen. Our function was WX plus B. We are going to find W and B values. I mean, this function is going to be mapped on the data set. So for initialization, we can set for the first values, we can set W and B equals to 0. And then for using gradient descent, we need to take derivatives. So the derivative of objective function or cost function, which we define it already here. You can see the average or cost function was equal to this one, W minus W hat, the difference between actual value and the prediction of the model. So we take the derivative of that function respect to the first variable, which gives you this one. Take again the cost function, derivative of cost function respect to the second variable, which gives us this one. Then we need to plug in new values to the old values. So you can say W would change to W old minus alpha, which is learning rate, multiplied by derivative of cost function respect to the W, to the weight. So here we are implementing this one. So def update W and B, X, W, X, W, sorry, X, Y, W, B, and alpha. It depends on 5 arguments. And then this step is in initialization. The first derivative of the cost respect to the W, I set that equals to 0. Then the derivative of the cost respect to the B, I set it to the 0. Then n equals to length of our vector, which is 200 here, and number of examples. And also we need to define a loop, because here is a loop. I mean, in every single iteration, we substitute or we plug in the new value of W to the old version. Then again, we take derivative equal to 0, and then plug the new value to the old value until we get the cost function in a way that the weight doesn't change, or the cost value or objective value doesn't change. So here you can see I used a for loop here for 200 example, which n is, and DL is basically equal to this one just. So, and DLB equals to this term here. Then for updating parameters, we are using W equals to W minus 1 over N multiplied by DL to DW multiplied by learning rate, which is just here. And we just implement the theory to the code. So let's run this one. Then the training will start. So as you have seen in the training, we had the function of training had 5 parameters or 5 arguments: X, Y, initial value of X, learning rate here, and epoch number. So I prefer to have 32,000 epoch number. So, and for running this, you need to press Shift and Enter, or press this button here. So you can see this going to train. As you can see, the cost function is decreasing. It starts from 2.6, 1.15, and it's going down. So if you follow these numbers, you can see it is stuck into 0.843. I mean, the loss or the cost cost values doesn't change over more iterations. So this means that training is done. So now let's plot the error versus number of iteration. So this gives you this, as I told you before. It means that after 1,000 of iteration, you can see the error doesn't change. I mean, it becomes kind of constant. So now even by looking at this one, you can find the proper number of epochs or iteration. I mean, if you train your model just over 10 to the 3 iterations, you can get the same result if you train it over 100,000 iterations. So because after this point, nothing's changing. After the point 10 to the 3, nothing is changing. Even if you continue, you might end up finding overfitting problem. So, and now here, what basically we are doing, we are just plotting the trained model over the data set. So you can see this line is perfectly fit with the data set. It means that every single data gets its minimum distance to the line we mapped to our data set function. So maybe now you can start from your side. I don't know running codes because I know I was so fast because I've already written those codes. So you can start from your own side. Then if some error rise.
Yeah. Two guys, they ask some question. What if we change the initial value of W and B and then we run it? I mean, that would be, I mean, ideally shouldn't change the loss function, right?
Yeah, let's do it now.
Yeah.
Let's say here we had X, Y, W, B. So WB was initially set to 0. Now I can change it to here. It was like,
yeah.
Let's say 1, I don't know, 1.4. Okay, let's go. I kept the rest, the learning rate, same, number of epochs, same. It seems nothing happened because you see we are getting the same error. But definitely it changed things. Now linear regression is super simple model, right? But just imagine that you have a deep neural network. I mean, the thing that we are going to see on the 3rd session. In deep neural network, even there are some algorithm, even you can see your initial error decreases, right? Because previously it was 12. Now it went to 4. And I'm sure if you plot the result, we can see good fitting. Yeah, you see. So, but when you're dealing with the complicated models, even there are some method exists for just initializing. One of the methods is that we are not just training the model once. We're training the model a few times, or maybe 100 times with different initial values. then we can decide which initial value is the best for training the model. Yeah, you had a really nice question. For really complicated models, defining the initial values is super important. And also defining the initial values of the weights, I mean the W's. Also here, I predefined the W's, you see, I defined the, here, I defined the W and B. I set them equals to 0, right? So even this becomes important when you're dealing with complicated models.
So if we, I mean, this if we don't, we're not very, I mean, very, I mean, deep, I mean, like deep inside this stuff, and just want to do it simply, we can just change it several times, and I mean, like, and the W and B, and see how's the outcome would turn out, right?
Yeah, it's one of the methods. You need to train your model based on different initial values. So it is the first step to do. I mean, let's imagine that the training time of your model just takes like 1 hour. So in a day, for example, if you have 8 hours, you can try 8 different initial values, right? But now imagine that if training of your model takes 1 month, I mean, which is really something true. Some models will take a month or maybe a couple of months. Then you cannot just using that simple method, I mean, changing initial value. Then there exists some sophisticated method, which even first try to find the initial values.
Thank you. So, thanks.
No worries.
So I don't see any question till now by the guys, but yeah. So yeah, I mean, anyway, if you had some questions, maybe later, if you tried and got stuck some problem, something, you can also ask tomorrow, and Dr. Abdolghader try to answer those questions. If we had something, I mean, later, if it came to your mind, and or maybe some question in the code later. Tomorrow also we have next sessions at 5 p.m. and on Friday also the last sessions again at 5 p.m. So if anything came to you and you couldn't ask today, don't worry, you can also ask it tomorrow. So I don't see any questions right now, but yeah.
It means two things. Either I was teaching super bad or everyone understands. So.
No, I think everybody.
But one thing, it's just an introduction to me as a personal experience. To me, it took like 2 years to learning these things. So sometimes, I mean, just 3 hours and 3 sessions, I mean, each 1 hour is not really enough. Maybe at the last session, I can share you all the online courses I took. So maybe it's kind of roadmap for anyone who is interested. So
Yeah.
because I also took like, I don't know, 10 online courses to just do my project. So for me, I was started with 0 experience about Python. So at first I started learning Python. So that's why, I mean, during these 3 sessions, you are just getting some intuition. I don't know, just seeing how things work. I mean, but don't expect yourself much.
No, that would be just some. Yeah, it's a very complicated thing. I don't think we can just cover everything, go very deep.
It's complicated, but the good thing is that I can tell half of my thesis was copied from GitHub. So you can also solve your problem because it's a big community. There are many people exist outside. They are willing to help people. I mean, it's not free helping because mostly when someone in GitHub or I don't know, in NVIDIA webpage, when they answer your question, they also get bonus. So the companies hire them. So it's not even free. They're not providing you free information. They're kind of showing up to the companies that we do have good knowledge. That's why, I mean, in Stack Overflow, you can see people that in a few seconds answer your question. So to me, at the first, it was like that. I don't know, they don't have any job to do, so they are just answering people's questions. But then I figured out that no, it's not free. Even they are getting projects. They are
from the
getting,
company.
yeah, offers from some good companies.
Okay, we have one question. Can you please give us some suggestion about the example data set that we can use to train models? Some standard data sets and this stuff for the linear regression?
Oh, a standard data set. Oh, I will find it something tomorrow. They should be on web. You can just Google it, finding some, I don't know. Here we just made 200 examples. I mean, super simple, but for sure there exists tons of data set that you can apply linear regression with the codes on the net. So everything is there.
So yeah, okay, maybe later at the end, maybe we can, at the last session, we can share some standard, those data sets, I think, for speech, for, yeah, speech recognition, or I don't know, different classification, linear regression task or stuff like that. But I think, yeah, you're right, there are so many free data sets that you can download from internet. Okay, so I think now we can conclude the sessions, and tomorrow we'll be back, I guess. So to continue. Thank you, everyone. Thank you, Dr. Abdolghader, for your time, and see you tomorrow.
See you tomorrow, guys. Bye-bye.
Bye.